Now the next part is that I told you when you're doing questions related to KP, there was one extra step that had to be taken, and that was KP was the ratio was the you had to calculate partial pressures. So that was one extra step that had to be done. It did not depend on moles. So these moles, we're going to use these moles, but we have to find the partial pressure. Now the way that was done was that partial pressure of N2O4 was calculated using mole fraction or the amount or percentage moles of N2O4 multiplied by the total pressure, which in this case is going to be your mole fraction is going to be one. I mean, what's the total moles? These are your equilibrium moles. So it's 1.5 out of 2.5. That's your mole fraction. 2.5 is the total number of moles, and 1.5 is the moles of N2O4 multiplied by the total pressure, which is 2 atmospheres. That's also given in the question. And similarly, you can find the partial pressure of NO2, which is again found using the same formula, mole fraction, which is 1 mole. So mole fraction is 1 divided by 2.5 into the total pressure, which is 2 atmospheres. So the moles of NO2 were these. So it's NO2 moles divided by the total moles, 1 divided by 2.5 into 2 atmospheres. And once you have that, you can use the expression, write the expression. What's the expression? For Kp, products over reactants, partial pressure of NO2 squared divide that by the partial pressure of N2O4, which is going to be 1.5 divided by 2.5 into, not this one. It's going to be 1 divided by 2.5 into 2 atmospheres. This would be squared. Divide that by 1.5 divided by 2.5 into 2. And you can try and can even try and calculate and tell me what the answer is. Just 1 second. किसने try किया? It's so 1 point. So for Sanjita, it's coming out to be 1.2. It's coming out. Nee, Sanjita, which, like the total thing? Can you calculate the total thing? Rida, Bhaskar, Minahil, did you try and calculate this?
0.533.
0.533. ठीक है. Two people are getting that. So this is coming out to be 0.533. As anyways, we can now start doing past paper questions related to this. I'm going to tell you two things. One is that uh, you don't need to, well, we can ignore that. We'll do one question and that will sort of explain everything. That's another worksheet. So I'm going to jump to these questions, and for example, let's start with this question. These are KP questions. Now the question is that at a pressure of 1 atmosphere, dinitrogen tetroxide is pretty much the same reaction, is 50% associated at a temperature of 60, and you have to find Kp. So, so now, and this is precisely the type of question that I wanted to actually solve. Uh, Remember one thing, that when you're doing Kp questions, even moles are not necessary. What is required is the mole fraction. Okay, remember what was the formula for partial pressure? It was mole fraction. I mean, it depended on mole fraction of a particular substance multiplied by the total pressure. So you don't actually need to know precisely what the moles are. Like if we go back and have a look at a previous question, for example, the first one that we did where we calculated, I mean, what we just needed was what percentage of each gas was present at equilibrium. So you could simply directly deal with percentages uh, instead of moles. And I'm going to explain how that could be done. So I'm going to just write this reaction over here, N2O4 in equilibrium with 2NO2. Now the thing is, I don't know what my initial moles are because he never gave me any. The question never gave me what was added to the container. You can look at the question. There is no mention of moles. I don't even know what the equilibrium moles are. So both of them are missing. What I'm only given is that under certain conditions at 60 degrees centigrade, 50% of this is getting dissociated, of N2O4 is getting dissociated. So I can start off with any number of moles. It wouldn't really matter at the end. For example, let's start with 2 moles. Let's say right at the beginning, I had 2 moles of N2O4 and no moles of NO2, right? I mean, there was dinitrogen tetroxide. So right at the start, let's assume that I had 2 moles. Now 2 is a hypothetical number. Okay, I've taken a random number, 2 moles. Now the question states that 50% got dissociated. So that means 50% reacted, which, what is 50% of 2 moles? 1 mole. So that means 1 mole has reacted. And if 1 mole reacts, on the other side, 2 moles are going to be produced. Like it's 1:2. So I took a hypothetical value, which is 2 moles, and I said that 50% dissociated, which means 50% reacted. Dissociated means that it broke down to form 2NO2. So 50%, and what is 50% of 2 moles? That is 1 mole precisely. So 1 mole reacted, so it's 1:2. So 2 moles got produced at the other end. So what do we have left at the end of the day in the mixture? It's going to be, you start off with 2 moles, 50% got used up, so you're left with 1 mole. On the other side, you had 0 moles initially and 2 moles got produced, so that's 2 moles. Now we've reached this point. Uh, what's the mole fraction of N2O4? That's 1 divided by 3. I mean, moles of N2O4 divided by the total moles, which are 3. What is the mole fraction of NO2? That's 2 by 3. Mole fraction of NO2 is uh, moles of NO2 divided by the total moles, which are 3. So it's 2 by 3. Mole fraction multiplied by the total pressure, which is 1 atmosphere, gives you. So this is my partial pressure for each one. So mole fraction of mole fraction of NO2 multiplied by the total pressure, mole fraction of N2O4 multiplied by the total pressure, which is 1 atmosphere. And what I can do is I can write down the formula for Kp, which is partial pressure of NO2 squared divided by the partial pressure of N2O4, which in this case would be 2 by 3 squared. It's going to be 2 by 3 squared divided by 1 by 3. And if you solve this, it's going to be, what would it be? 4 by 9 into,
C.
so it's going to be C. So this would be, yes, it's coming out to be C. But now the issue is, what I wanted to state precisely was that I took this initial 2 moles. Even if I had taken a different amount of moles, the answer would still come out to be the same. Because mole fraction is going to come out to be the same. I mean, we can try doing this entire question, and this time my starting moles are going to be different, and we'll see, or we'll try and figure out whether are we getting different values or not. So let me rub this off. So let's start with initial moles being 10 moles. So let's say my initial moles were 10 moles of N2O4, nothing of NO2. 50% got dissociated. So 5 moles reacted. On the other side, they're going to produce, it's 1:2, so 5 would produce 10 moles. So out of 10, 5 have dissociated, so you're left with 5 moles. And 10 moles of NO2 have been produced. So these are my moles at equilibrium. If I try to find mole fraction for this would be 5 divided by 15. It's 5 moles of N2O4 because 50% got dissociated. So you started off with 10, 50% are gone. So your remaining moles are 5. So 5 out of the total moles at equilibrium are 15. So what is this equal to? This is still equal to 1 by 3. And mole fraction of this would be 10 divided by total, which is 15, which basically comes out to be 2 by 3. So you're getting the same mole fraction. And so everything, the end result would be that your expression is going to come out to be the same. So my only point is that, and let me go back. Where's the, not this. Okay, so let me go back and stress this point again. The point was that the actual moles don't even matter in this case. If you have, if you're able to get mole fraction, uh, then you can precisely find Kp. You don't actually need the actual number of moles. So this next question is very similar. Again, he's saying that 20% of the steam is getting converted into hydrogen and oxygen. So I'm going to write this, I'm going to do this question, because at the end of the day, I just need the mole fraction. Like, what mole fraction is this? I mean, your equilibrium is going to contain all three. What percentage is going to be this? What is the percentage of H2 in that mixture? What is the percentage of O2 in the mixture? So you start off with 2H2O. So now I'm going to start off with 1 mole. Let's say initially I had 1 mole. no water was produced. This is wait a second. This is hydrogen. So right at the beginning, no hydrogen was present and no oxygen was present. So 20% of the steam is dissociated. So out of 1 mole, 20% is dissociated. What is 20%? So that means 0.2 reacted, right? So you're left with zero point 0.8 moles. 20% is gone. So you're left with zero point 0.8 moles. Now, if zero point 0.2 react, on the other side, they're going to produce 0.2 moles. That's the amount that's going to be produced. And 0.1 moles, according to the ratio, 2:1, 0.1 of oxygen gas would be produced as well. So at equilibrium, you're going to have 0.2 moles of this and 0.1 moles of this. So you found your equilibrium moles. So 20% is getting dissociated. So 20% is getting dissociated, and so out of 1 mole, you're left with 0.8 moles, and the 20% that has reacted ended up producing 0.2 moles of H2 and 0.1 moles of O2. Is this clear to everyone? Bhasga, is this clear? Minahil, is this clear? Okay.
Yes.
Achha, so the thing is, we found the moles at equilibrium. Like these are hypothetical moles. These are just, I mean, you could have taken any value. Okay? You could have taken 2 moles initially, taken 100 moles. Uh, the end result is, how do you find partial pressure? Partial pressure is mole fraction. So what is mole fraction of this? It's 0.8 divided by the total, which is, what is the total moles? 0 0.8 plus zero point 0.2 plus zero point 0.1, so that's 1.1. What is mole fraction of this in the mixture? It's 0.2 divided by the total, which is again 1.1, and mole fraction of this would be 0.1 divided by 1.1, and this needs to be multiplied by the total pressure, which is given somewhere. It's given over here as 1 atmosphere, so multiplied by 1. So the question wanted us to calculate the partial pressures. So it's mole fraction into total pressure, which we have done over here. So the correct answer is going to be, it's probably going to be D. Okay, D is going to be the correct answer to this question. Now let's do a few more questions. Remember that the value of Kp or any equilibrium constant only changes with temperature. So you're going to get a lot of questions like these. So we can. So this question, let's try and do this question. The question stating that, and again, it's the same one that's repeating over and over again. So I'm going to, just for the sake of the table, I'm going to write this over here, 2NO2. So now in this question, they've given us exact moles. So use those. 2 moles are initially added. 2 moles of dinitrogen tetroxide. So these are added to the container. It says it's sealed in a container at 350 Kelvin. So 2 moles were added. So this is your initial. No NO2 is present. And then at 140 kilopascals, the mixture gases contained 1.84 moles of dinitrogen. So when you open the container after a bit of a time, he found out that 1.84 moles of N2O4 is present, which indicates like initially you added 2 moles, now you have 1.84 moles. So that means how much is missing? 0.16. 0.16 moles is gone. It has reacted. So what would it produce if it reacts? It's going to produce NO2. And how much? 0.32. That's the amount that's going to be produced according to the ratio, which is 1:2. So 2 moles initially added, 1.84 left at the end of the day. I mean, it's stated over here. So that means 0.16 got reacted. 0.32 are going to be produced. And you can, and at equilibrium, it's also going to be 0.32. So these are your equilibrium moles. Is this part clear so far? Yes or no? Is this clear?
Yes.
Yes.
I say, so first thing was write the expression for Kp. Kp was, I mean, product over reactant. So it's going to be P N2O4. Divide the whole thing by P NO2, and that is going to be squared. I said calculate the number of moles of NO2 present at equilibrium. We did that already. Calculate the number of moles of gas present at equilibrium, hence the mole fraction of each gas present. So we need to find the mole fraction. So it's going to be these moles divided by the total moles. So it's 1.84. Can anyone do the calculation? 1.84 divided by the total moles, which are, what is 1.84 plus 0.32?
2.16.
Okay, so this is 2.16. 2.16. And this would be 0.32 divided by 2.16 again. Anyways, we found the mole fraction of each gas. What's the next part he's asking? He's asking calculate the partial pressure of each gas present at equilibrium. So to calculate partial pressure, you need to multiply the mole fraction by the pressure, which in this case is 140 kilopascals. ठीक है, it's given over here. 140 kilopascals. That's provided over here. No need to convert kilopascals into pascals or anything. Just multiply it by 140, and you will get the answer in kilopascals. I mean, this value would be in kilopascals. The partial pressure of this would also be in kilopascals. And the last thing that you had to do was you had to calculate the value of Kp. So we can simply put these values in the expression that we already have with us, which is what's the expression? It's N2O4 divided by NO2 squared. So it's 1.84 divided by 2.16 into 140 kilopascals, and you're supposed to divide the whole thing by the numerator, which is NO2 squared. So it's 0.32 divided by 2.16 into 140, and this entire thing has to be squared. Okay. And that's your value for Kp. Can you even tell me what the answer is?
0.277.
0.277. So the question is, if Pascal was given, then what we would do? Yeah, I told you that if everything is given in, if they're talking in terms of kilopascals, keep everything in kilopascals. If they're talking about things in pascals, keep every. I mean, there's no need for conversion. Similarly, if they're talking about it in atmospheres, keep everything in atmospheres. Sanjita, is this clear? And so one thing that you had to do was include the units as well. Now remember our units. I mean, we're going to come to this. Remember that we are dealing with kilopascals. So it's going to be, I mean, our unit is kilopascal divided by kilopascal squared. So it's kilopascals to the power of -1. That's going to be our unit. So I'm going to add that unit over here. TK, you can have, it's going to be kilopascals power -1. TK. Now we're going to move to another question, which is, so let's quickly do this. You think, right, the expression for the equilibrium constant Kp. Now it's fairly easy in this case. It's products which are PNO 4 multiplied by PH2O, and that's going to be power 6. And these are being multiplied, right? Divide by PNH3, and that would be power 4 as well. Multiplied by the partial pressure of O2, and that's going to be power 5. And you have to come up with the unit as well, which is uh, on the numerator terms are 10, the denominator terms are 9. So the unit is, I mean, he's using kilopascal, so I'm going to use kilopascal as well. Kilopascal power 1. I mean, it's x to the power 4 into x to the power 6 divided by x to the power 4 into x to the power 5. So you'll be left with x to the power 1. And that's kilopascal to the power 1. I said this is about Lee-Shatler principle. So let's do that. What's going to happen if you increase temperature? Whenever you increase temperature, what reaction is favored? The endothermic reaction is favored. Which, if you look at the delta H, it's negative. So that means backward is the one that's endo, because the forward is already given as exo. So what would happen to the yield of NO? It's going to drop. It's going to be lesser. It's going to decrease. Why? Because backward reaction is happening. Because backward is endo. And whenever you increase temperature, the endothermic reaction is the one that's favored. And if you decrease pressure, what happens? More gas would be produced. More gas mole side is favored. So more gas mole side is favored, and which in this case is which side has more gas moles? Again, it's the forward. Forward has more gas. So if you decrease applied pressure, more gas mole, more forward reaction would happen. Hence, more NO is going to be produced. So now everyone, I'm posting this question. Everyone, try and solve this. I mean, I'll give you the equation as well. I think it's the sulfur dioxide and oxygen in equilibrium with SO3. everyone try and solve this, and you have to give the value of kp and its units as well. So everyone, is this clear? The last questions. Any questions about this? Try and so quickly try and send this on WhatsApp. Okay. This question. Try and quickly solve this. Okay. This is probably the last question we're going to do for KP, and then we're going to move forward. So okay. Okay then. Take care. This week I'm also not 100%. Uh, hopefully, okay, things are looking good. So uh, extra classes probably weekend के ऊपर ठीक है. The missed classes can be done on the weekend. चलिए, okay, take care. Allah Hafiz.